Okay, so now let us consider an example of simple harmonic oscillation in a case other than mechanics. So let's talk about a LC circuit. So what is a LC circuit? Well, that L here is for inductor and C is for capacitor. So a LC circuit is actually a circuit containing an inductor and a capacitor. So let us draw a simple LC circuit here. So let's say we have our capacitor here, okay, and it is connected with an inductor. So here is our inductor. Let's say of this capacitor is C and the inductance of this inductor is L. Now, as you know that a capacitor acts like a source of charge. So let's say when it is in charge condition at the initial stage, let's say here we have charge plus Q and here at this plate we have charge minus Q. Now when this is connected to this inductor, charges will flow through this inductor in this direction. So there will be a current in this direction. Let's call that current I. So there will be a current in this direction. Now all these things, this plus Q, minus Q and I is actually function of time, okay, because they vary with time. So they're a function of time. Now let's talk about the potential difference between these 2 points. Okay, so let's say we have attached a voltmeter to find out the potential difference between these 2 points. As the capacitor here and the inductor is connected parallelly between these 2 points, the potential of the capacitor and the inductor should be same. So remember the equation of the voltage difference due to a capacitor. What was that? Well, it was Q over C. Remember, this Q is a function of time. So this is the voltage difference across the capacitor, and the voltage difference across the inductor is L, rate of change of current with respect to time. That is L times di dt. Now here the current is actually also a function of time as well. Now as they are connected parallelly, so you can see between these 2 points, so the potential difference is actually equal. So we can write them down as to be equal. Now, if you are not familiar with these equations, I would suggest you to have a small review of capacitors and inductors. I will also add some videos with this one, which will give you an intuitive understanding of how an LC circuit works. Okay, so now let us start working with this equation. Here the current I through this inductor, well, we know that we can define current to be the rate of change of charge, right? And where does this charge come from? Well, from this capacitor. So actually the capacitor is losing charge and it is flowing through this inductor, right? So we can actually write down this current I here to be equal to minus dqt dt. Again, this current is a function of time. Okay, so let us use this thing in this equation. So what do we have here? Well, we have on the left hand side Q, function of time, over C, L. Now already current I is minus this quantity. We can write this as minus Q dot of t, right? So again, differentiating this one, we can write this as Q double dot as a function of t, right? With a minus sign. Now, if you rearrange this equation, what do you get? Well, we get Q double dot plus 1 over LC times Q, okay, equals 0. Now, this differential equation, well, it should look familiar to you because this is the equation of a simple harmonic motion, right? So that means this Q here, the charge across this circuit, okay, is going through some simple harmonic oscillation. And what is its frequency? Well, this term, it is called the resonating frequency, right? We had omega squared here, so here omega squared is 1 over LC, so that means omega is 1 over square root of LC. We call this the resonating frequency of this circuit. Now, if this is an ideal circuit and there is no resistance in the wires, this simple harmonic oscillation would go on forever. Now, as in the case of a simple pendulum or a spring mass system, the kinetic energy and the potential energy converts to each other. So there is some kind of oscillation of the energies. Kinetic converts to potential energy and potential energy converts to kinetic energy. Here, in this example, what happens is the electric energy of the capacitor converts to the magnetic energy in the inductor, and the magnetic energy of the inductor actually converts to the electric energy of the capacitor. This kind of back and forth oscillation is going on here, and this gives the total energy a constant if there is no loss due to any kind of resistance. Now let us have a look at what the solution of this differential equation would look like. So again, we can say that the solution of this equation, Q as a function of t, would look like something like this. Some constant times cosine of omega t plus phi. Now this is Q. Then what is current I? Well, current I is just Q dot, right? The rate of change of current with time. So we'll have here a omega minus sine omega t plus phi. Now you can see from here that current and this charge, they are 90 degrees out of phase with respect to each other. You see the cosine term here and the sine here. That is from this equation, when we can see that when I is equal 0, what do we have for Q? Well, I0 means sine this is 0, and sine 0 means cosine of 0 equal 1, or we can have minus 1 as well. So we'll have plus minus a. Now again, if Q is equal 0, so that means this thing is equal 0, we'll have current I equal to, again, plus minus omega a. So you can see the 90 degrees phase difference between Q and I from here. Okay, so now let us find the total energy of this LC circuit. Well, the total energy will be the sum of the energy of the capacitor plus the inductor, right? So the energy of the capacitor is half CV squared, and for the inductor it is half Li squared. Now let us use these solutions in this equation. So let us first express this in terms of the charge Q. So we'll have half Q squared over C, right? By using this relation here, plus half Li squared. So now if we put this value of Q and I here, what do we get? Well, we get half A squared over C cos squared of omega t plus phi, right? Plus half L. From here we can see A squared omega squared sine squared of omega t plus phi. Okay, now what is this omega? Well, this is the resonating frequency of the circuit, so we can write down omega to be equal to 1 over square root of L. That means omega squared is equal 1 over LC. So this again gives us A squared over C. So you see the similarity between these two things. So if you take this thing common, what do you have? Cos squared of some angle plus sine squared of some angle. So that means it gives us 1. So we'll have half A squared over C. And as you can see, this A and C both are just some constant. So the total energy of this system is actually constant. So this is equal constant. Now what does this constant A mean? Well, from this circuit you can see that just when we connected the capacitor and this inductor together, all the energies were due to this capacitor because there was no current flowing through this inductor. So that means this Li squared was 0, so all the energies were half CV squared. Okay, so that means in that situation the charge here was the maximum. Okay, so we can write down this total energy to be equal to half Q max squared over C. So this means that we can write down this constant A to be equal to Q max, which again we can write down as C times V max. So the total energy here can be also written as half C V max squared. Okay, so this was an example of simple harmonic motion outside the scope of mechanics.